Welcome to the first lecture of Deep Learning for Natural Language Processing in summer semester 2021. My name is Ivan Habernal. I'm super happy to be here virtually. So in this semester, I will be your lecturer as well as your YouTuber. So the general terms apply. If you like what you see, you can give a like. You don't have to. And you can ask questions here in the comments, or you can ask on the Moodle and other forums. I'll get back to that later. In today's lecture, we'll talk first about some administrative issues. I'll try to go through that quickly and then go to some interesting stuff. For example, why deep learning is important for natural language processing, or even why is there natural language processing without deep learning? So very little. And to some basics later on as principles of neural networks and some activation functions. But first, let's start with some administration. So I don't have to convince you to take this course because you have done it so far already. But what are the learning goals? What should you be able to learn after completing this course? Is actually to understand what makes neural networks so powerful and why they are so successful in in natural language processing. You will understand some concepts such as word embeddings. Or how can you use deep learning for solving some typical NLP problems such as text classification or sentence classification or sequence tagging, which is somehow special to natural language processing. And you will be able to implement some of these algorithms using some existing frameworks in Python. And you should be able to actually understand the overall hype. So if you read a new newswire paper about GPT-3 is so powerful and it's almost as good as intelligent as humans are, you should gain some skepticism here and to understand how actually, for example, GPT-3 or other transformer architectures, how they work, what they can do, what their strengths are and their weaknesses, and really understand the basics and the core principles of these algorithms. So we're running Moodle for lectures, submissions, and so on. So the teaching materials will be there. Also, we will be publishing the slides under permissive license, so everybody can use them freely. So we will be using the license CC by share alike, and these are in Beamer, which is LaTeX. So anyone can download the source codes of these slides and reuse them, provided you pay attention to the license and extend and make your own notes and so on. So I'll be putting this on GitHub. But we're using resources for this course that are based on some recent NLP conferences or papers from recent NLP conferences for one reason. The field is evolving super fast, super quick. So what has been a breakthrough, for example, 2 years ago or 3 years ago, for example, the BERT models by Jacob Devlin and others in 2018, basically in 2018 and 2019 got published. It's now considered mainstream or even not obsolete, but it's super mainstream and it's just 2 years or 3 years old. So it's evolving super quickly. Though there are some resources which are in terms of textbooks or books which are super helpful to get some background information. So I would highly recommend to have a look at this Ian Goodfellow and others book called Deep Learning Creatively, but it's a very good book actually. It's very thorough, very fundamental. And the advantage of that is you don't have to buy it. It's freely available, done by the authors as HTML on this site, deeplearningbook.org. So you should have a look. There are a couple of YouTube videos by Richard Socher from Stanford. So you can look it up on YouTube. There are many materials on YouTube actually, by the way, of different qualities. There is another very good book for this course called Neural Network Methods for Natural Language Processing by Yoav Goldberg, who is one of the leading researchers in the area of NLP and deep learning. Unfortunately, this book is not free. So there are versions of this book on archive, on preprints, but there is no one-to-one version of the book published by Morgan and Claypool Publishers later on. But if you want to invest, this is a good book. And there are two other ones which are very relevant if you want to dig deeper, and we'll dig deeper in some lectures, so you might want them useful. One of them is Mathematics for Machine Learning, which is also freely available as PDF by authors, and there's a printout version from last year, but the authors make new versions publicly available on GitHub, and they update issues, and you can clarify question in the issue. So it's a very, very thorough book and very nice. I guess it's going to be the Bible of mathematics for machine learning. Very well written. And if you feel like mathematics could be something like sounding a little bit of Chinese for you for some reasons, I mean, you like mathematics, but sometimes it's super confusing, and you struggle what they're writing and why and so on. I found the last one here from Jeremy Kuhn, this book, actually pretty cool, because it's a programmer's introduction to mathematics, and we are computer scientists also. We like to build things. So he took a perspective of somebody who is a good programmer and tried to disentangle the field of mathematics, which might be confusing because of some ambiguity and so on. So it's really cool book. It's not only introduction, it goes as far as group theory. And you can get it legally for whatever you pay. So it's a very nice read. I can recommend it as well. We will provide a list of relevant literature or papers, or except for no papers, to each lecture. I guess we'll put it on Moodle, and there will be topics covered in this relevant papers that are relevant for the final exam. There's also some additional background reading, not important, but it will make help you understand better the topics just discussed. So we encourage to read that. If you have any questions by getting these publications and so on, just ask in the Moodle. Then we will talk about exercises and homework. So we have two different hands-on experiences in this course. One is exercises, and exercises are not graded. Well, it doesn't mean they are not relevant. So I guess you should give it a shot and try them out, because they will make you understand by actually doing what we're talking in these lectures. And you will get your hands dirty and try things out, which is super helpful. Exercise and homeworks are actually they are graded. So homeworks, you will get points for them. We decided this year to do it in groups of 2. So you will form groups, and you will work together on these exercises. They will be mostly programming, maybe some math and paper reading and so on. And the main organizer is Jonas Rejkowski, so he's in charge for exercises and homeworks. We have a platform for discussing, so apart from the obvious Google comments, where I'll be monitoring that as well, we have a Moodle forum, so the classical old school one from TU Darmstadt. And we thought like, well, okay, everything is virtual now, so students are not seeing each other that much, and maybe you're not really want to publish your maybe stupid questions to the Moodle forum. There's no such a thing as stupid question. Just ask whatever you really need to dig deeper. We have a Discord server set up. So if you're a gamer, you're familiar with Discord, super easy to work with, chatty. So we have a Discord server, and we put a link to that on the Moodle. And after this lecture, I really recommend to read Jonas Rejkowski's logistics PDF about the exercises and homeworks, and all the details how to get the groups. Apart from these two exercises and homeworks, we also have a shared task. So what is a shared task typically, if you're not familiar with this term yet? Means there's a problem described as a task, and typically you have some data set where you can train your models or whatever you don't want to do, and then you can evaluate it and get a score, and the scores are ranked. So it's like, if you know Kaggle, it's basically the same thing. So there's data set, and you submit your solution and get some points. We thought by last year's experience it could be fun to do, because it's done in groups. So it's a teamwork up to 3 people, and the topic we selected for this year by my colleague who is also giving part of this lecture, Mohsen Mezga. So he's researching on conversational AI, so chatbots or dialogues, and we thought this could be really, really interesting, so to say, use case, because it's very fresh research-based topics, but also it could be fun because you see some basically dialogues being generated by the system you work on. So we thought, let's give it a try. So Philip Marquardt will be the contact person for this shared task, and as usual, all the details will be on Moodle, and so on. So there will be some points for that, and so on, competing with others. All these things are a bonus system. So by doing your homeworks and not the exercises, the homeworks, and participating on the shared task, you will get some bonus points. And once you reach some certain amount of bonus points, you will get a plus for the final grade. So I'll get to the final grade later, but just you know the names. Jonas Rykowski and Philip Marquardt are responsible for the exercises and the shared tasks. And again, Moodle, Discord, and so on. So the final exam we will get someday later on, so it will be published on Moodle. It will be in English, and you can answer in English, you can answer in German. Most importantly, you have to answer somehow we can read it, So last experience from the exams, I had sometimes really hard time to understand what people are writing. So you can use this time before the exam for practicing a little bit of handwriting. But I have to say my handwriting is also terrible. So if I write something here which you don't understand, that's I'm sorry for that. So I'm really bad in handwriting too. But you have to do it on paper in the exam. So give some time and give some patience and love to handwriting, so we can really understand what you're trying to say in the exam. You can use some other stuff for the exam. So like a dictionary, if you if your English, neither German is your first language. You can use dictionary, that's fine. We will, the final grade will be 100% exam, and then bonus is a plus. So you don't have to do anything extra. Just show up for the exam and get 100% scores. You get a grade. That's perfect. But the bonus is really, all these exercises and shared tasks are super helpful to get hands-on experience. You can also bring a non-programmable calculator. For the exam, I don't expect to do any hardcore calculation, which couldn't be done on back on the envelope calculations. And actually, I don't even know if anyone has this is a calculator, a smartphone, but you can't bring that. So if you need a calculator, bring it. Okay, and no other sources are allowed, which is just a standard thing. Given we have very limited kind of interaction, I hope I will see some of you later on, at least by the exam, and we can talk a little bit, but there's very little feedback from your side to our side, or to the lecture, to the exams, and so on. So please use the Moodle forum, use the Discord. I'll be super happy to chat on Discord. You can write emails, that's fine. Don't overdo it with emails. Emails is if you write an email, it's my to-do, and I don't like it. But if you write on Moodle or Discord, there's a chance somebody will jump in and discuss that. Now it brings me to a little bit introducing my research group called Trustworthy Human Language Technologies. We do two different sort of streams of research. And one is the methodological, which is NLP with privacy preserving. So what does it mean? We do care about privacy. Some people don't care about privacy, and that's fine. So we can do research on that. And especially in particular on differential privacy and deep learning, how to learn representation of text to keep an eye on privacy of individuals, maybe in graph on social networks. So this is a very hot topic, very interesting, and goes very deep into learning representation. It combines what we're learning here, for example. Another stream of research seems to be more applied, and it's called, I call it argument mining that matters. So argument mining to me is finding arguments in discourse, in text. Could be arguments to some topics that are of importance, but I think finding arguments in, for example, in legal texts, so in jurisdiction, in decision of the court, might matter quite a lot. If you're really interested in finding good arguments that work in the court, for example, in human rights, this is one project we're working on. It might be might be a good domain to work on. Or maybe like ethical arguments. So as a researcher, we talk quite a lot about, well, is it a good technology or is it bad technology and so on, but we don't really understand quantitatively how much we talk about it. So we're trying to mine some ethical arguments in that. If you're interested in any of these topics, just drop me a line, get in touch, and I'll be happy to talk about it. Or even better, if you're interested in master thesis, just get in touch. I don't have so many open topics, but if you're interested, just drop me a line, and we'll try to find. Provided you finish this course with a good grade, because basically what you're gonna need is deep learning and NLP, because this is the mainstream, and everything starts with that. So now we're coming finally to this lecture's actual content, and this is deep learning for NLP. We'll start with perhaps abstract, high level. What is deep learning? So this is a subfield of machine learning where we use basically neural networks, and the neural networks are large or deep, so this is why we call it deep learning. Natural language processing is analyzing language in many different forms. So deep learning has been here actually for quite a long time. So, from early 1950s, we have this first something, like architecture which could be considered as neural network, Perceptron. We will get to that in detail later in this lecture. So we consider, 1958, it's 60 years here. So it's barely boom. There was some serious setback in the 1960s and 70s. So that people found out like Perceptron is nice, it can learn some representation, but it doesn't really work for other complex functions. Then it came 1980, so backpropagation and actually deep networks, and it went out of fashion in the 1990s because new techniques came to the place, such as support vector machines, and there's some anecdotal evidence of Geoffrey Hinton, one of the leaders of deep learning back in the days, or still one of the leaders of the field. He said, if you even submitted deep learning papers to computer science journals, they would be rejected because it was just out of fashion. And then, since 2000, there was again progress in deep learning, and again Geoffrey Hinton and others showed that you can train them well with some pre-training and so on. And then came the boom in 2010, 2013 with word embeddings, and now we're on the hype. Why is it interesting? Well, you could see that research is done as a community effort, which means even though the ideas have been the same all over the 60 years, it's a perception in the community which makes it somehow shine or not. For example, this out of fashion 1990s, because there were other, people didn't believe in do that anymore, and they thought let's invest research into something else. And some people persisted and showed 20 years later that it actually works. Why is that so later on? Because we have more, the three pillars of success of deep learning are faster computers, GPU, super much more data, internet, and some better optimization techniques, and unsupervised pre-training of the data. So learning some representation in unsupervised manner. This is really what helped for image recognition as well for NLP, word embeddings, for example. And if you look at research in NLP, now it's kind of obsolete, right? 2015, it's 6 years back. So I guess, that the trend would be nowadays skyrocket, if we have 2020 here. But you could see, zero research here on neural networks. And now basically everything which is in NLP is deep learning based, mostly. So you can't go away with that. And it made it mainstream. So basically what we are doing now has been 5 years ago, something fresh course and something, edge technology. Nowadays it's considered mainstream, and you have to know it. Why is that so? Well, deep learning actually worked better on the task we considered important. For example, in in NLP machine translation in one of the tasks, and the old approaches were called phrase-based machine learning or statistical phrase-based machine learning, and they were only as good as some scores. And humans are considered the top, humans are considered the best translators. Depends, of course, on the languages, as we can see here. And neural networks just make it so much better over the phrase-based that, well, they can compete with the human translator in some cases, and they're, getting towards human performance. I have to say, it's very, it's important to know what these tasks are, what they mean, and what these scores mean. So being good in translation, for example, in French English, doesn't mean the computer understands language and could do anything and, being a new Terminator. So if you read some newspaper articles about GPT-3, like human performance, be always skeptical and check the tasks that are actually, being measured. And what is being measured is not really what we feel the intelligence could be. We'll get back to this evolution metrics, I guess, in the next lecture as well. And of course, not everything works if you have a powerful big hammer, which is a neural network, but some things could be difficult, some tasks could be super difficult, and if you don't have so much data sets, maybe you cannot do anything with deep learning. Maybe you could with some pre-training and so on. And other critical parts are considered a little bit of black boxes of deep learning. So, how can you explain the predictions of deep learning network, because there's just so many parameters. And this is one of the hot research topics nowadays, explainable AI, they call it. And you can fool the networks by adding maybe some random noise. So for example, here it's not from NLP, but from image recognition. But here we have an image of panda, and the network said, okay, well, I'm 60% confident this is panda. And the researchers just added some random noise, which it's really random, or it has some properties, but it looks random, at least to humans. And the result is still, for us as humans, well, this is a panda, right? And they found that they can fool the network to guess this is a gibbon with very super high confidence. So, these networks are kind of brittle, and you can trick them into doing something which they weren't trained on. And the same thing is, for example, privacy. So, you can maybe learn original data from the network. So this is something. I guess there will be some lecture on it later on. How can you find out private information from network? So we were talking about different tasks. So let's show a couple of NLP tasks, some low level and high level. So we know, what the problems can we have a hammer, which is the deep learning or neural networks. So we need the nail, and the nails in NLP could be, for example, sequence tagging. For example, part of speech tagging. So part of speech would be, for example, verb or noun and so on. So here's an example of two sentences. Time flies like an arrow, and it's very ambiguous because it can have different meanings. Just give it a second, think about it, and there's so many different explanations of this sentence. And fruit flies like a banana. So one example could be that time is a singular noun, fly is a verb, like is preposition, or it's a conjunction here, and arrow is again noun. So these are the part of speech tags, and you want your network to predict these as a sequence for your sentences. Or another NLP task could be syntax parsing. So here we have a constituencies syntax tree. I guess everybody's doing that in a language lesson in a grammar school, right? So the sentence is breaking down into noun phrase and verb phrase and so on. So we basically have a syntax tree of these two sentences. And here you could see like the different implementations, different interpretations or syntax interpretations of the same sentence. So parsing or chunking go into structure prediction, and we want to predict the structure. Why do we want to do that? These tasks have been traditional for many years, And the community believe that if you do proper part-of-speech tagging or syntactic parsing, it will help you for more high-level tasks later on, like machine translation. As it turned out, you can do machine translation with neural networks without actually taking care about the syntax or part-of-speech explicitly. But these tasks are important because they reveal something about the linguistic structure of the language. Another low-level NLP task is words and disambiguation. So again, time flies like an arrow. So we might consider time as one entity here, or one sense of the time, and flying and an arrow, and basically you would assign a sense from some sense dictionary to all of these words. If you find these first examples kind of boring and very low level, I understand that. So there are some high level NLP tasks that have some actual clear use case right away. So information extraction, searching in text, finding events in text, spell checking, grammar checking, and writing assistance is super helpful task because it helps you write without errors. Text classification is a field for itself. For example, spam classification, it's still an issue, so you have to still adapt your models for classifying spam, or finding sentimental free views, and it's a classical one. Natural language understanding means more understanding deeper on the language, maybe not in the sentence, but maybe on the discourse level. So finding maybe arguments in the text, or question answering. So for example, you have a question, you type it in natural language, and the system will answer you in natural language as well, and the correct answer. So this is a very nice use case, and it's like also industry ready. So you can see examples of that already in production. Natural language generation is interesting. For example, in chatbots. So in a chatbot or conversational AI, you not only need to understand the language, so what the user is saying, you have to also generate a response, and then also you have to keep the flow, so understand the whole context of the discussion. It's super hard task. And again, the multilinguality or machine translation task, as we already show, everybody knows or using Google Translate, which has been using neural machine translation for some recent couple of years. It's a tool of the day if you really need to translate something from the language you have no idea what is it about. It's super helpful. So here we will demonstrate one particular task called named entity recognition, and how it's done traditionally without deep learning, and then how deep learning can solve it. And just to introduce what this task is actually about, so named entity recognition, provided this is a text, so Chancellor Angela Merkel said something, so on, so on. So if we do named entity recognition or named entity tagging, we have each word associated with a particular entity. So Chancellor is no entity, that's why it's 0. Then we have Angela Merkel, which is a entity for us. It's an entity of type person. And how we tag it in the text, because we have split it into several tokens, we say, okay, this token is the first one, so B is the beginning and E is the inside. So using this BIO tagging, you can uniquely or unambiguously assign a label to each word in the sequence. So then you can learn a model to predict that. So again, B is the beginning of the entity. So B person is the first word of the entity of person. So this is the person. And E is the inside. So again, E person would be the tag for the word, or E location, inside location. And the O is for other, so words that we don't consider as entities, so they don't matter. So basically then each word is associated with one tag. How can you do that? So for example, now you want to predict the tag for word Angela. And if you know machine learning a little bit and you don't know anything about deep learning, you know that each prediction can be, you have to use some features to describe your instances. So typically you would have some features, for example, is the word uppercase, yes or no? So Angela is uppercase, yes, okay. Is the word noun? It is noun, yes. So what is the previous word? Is it determiner? Oh no, it's no determiner. Previous word, is it uppercased? Not really, no. Following word, is it a noun? Yeah, it is. It's Merkel. Okay, good. And is following word uppercased? Yeah, it is. Okay, and so basically you would create your feature vector for this instance, and you would feed this feature vector as the input for any classifier. As you might see, finding all these different features is actually time consuming, because you have to think of, okay, what else? Like maybe two words, maybe not only the previous word, but maybe two words before we have to extract features as well. So it makes the feature vector extraction super complicated, and of course very sparse, because you have to have much more data points to learn mapping from features to something which is, for example, be person. Or some other, because you have all these text sets, so you can have, I don't know, let's say 200 tags, and you wanna, based on these features, you wanna learn which tag is that. So you need to learn this. You need to have enough statistics. So it makes it complicated, and also finding good features which are sort of powerful. So another example, continuation. Now we're in numerical. So the next word, prediction, and again, we extract the features. So it's uppercase, yes. It's noun, yes. Previous word is determiner, no. It was a noun, no. Previous word was uppercase, yes. We have a. Following word is verb, no. It's not uppercase, and so you get a gist, right? So you're extracting little features for each word, and then you would feed them into a classifier. But creating this feature extraction, it's a hard job, and before deep learning, people spend a lot of time finding good features for each NLP task. Another issue with that, apart from doing this manual feature extraction, all these features, is that similar words would have like different features, like distinct features, because they live in, they are not. There is no notion of similarity of words, because we have a vocabulary, and each word has different position. So, for example, if previous word is minister, so this is some classes, but let's say the previous word is specific word Angela. Okay, so there would be one feature, and then it would say previous word is a dot, because you can have text Angela Merkel and a dot Merkel, and these two features would mean the same thing. Like the previous word was perhaps, or there is some similarity between previous word Angela and previous word a, but our typical feature extractors wouldn't capture that, unless we have some classes of, for example, previous word is a product, or previous word is something. Deep learning is trying to fix that, and it's trying to do multiple things at once. First, it's trying to learn some notion of similarity between words. So we will find that some words are closer to each other than others. Also, it tries to extract the features automatically. So what you have in the input is just the plain text, and you let the network extract features while learning something. And you let it predict your, what you want to predict. So, for example, the classes in name recognition. So we're starting with the oldest neural network architecture called the Perceptron. It's a very simple model, as we will see, but could be very powerful in some cases, and used to be very powerful in some setups. It's dating back to the 1940s, 1950s. And it's for learning a binary classifier. So the output would be 0 and 1, false or true. How does it work? So let's say we have the input is in form of some features. So this is the feature vector. And so the perceptron knows that each feature at each position is associated with some weight. So these are weights. And what is it doing? There is a first something called pre-activation, which is weighting each of the input feature by its associated weight. So it's some weighted sum. So it takes the first one, multiplies with first weight plus the second feature times this weight, and so on. And we have this very weird term b and 1. So why are we doing that? So imagine that you have all of these are zeros, but still you want to output some real number which is not 0. So we have this term b. So it's something in the absence of input, we will still have some activation of that. So this is a linear combination. It's nothing more than a linear combination of the input features plus some term b. And a linear combination of features will output it's a linear map. It will give you some real number. And we have something called activation, which adds nonlinearity. So this sigma function is a nonlinear function which do some nonlinear transformation with the output. So again, this here is linear. So up to here is linear combination, and here is nonlinear because you want to squeeze this output. Now, very concretely in mathematical terms, is we have the vector, which is a vector of these weights, and we have the bias term, and we have some nonlinear function which maps from a real number to a real number. The input to the network are these point x, the features, which lives in the n-dimensional space, and we have this constant 1. And we have the output unit. So first, the pre-activation is basically dot product of these input features and the weights plus the b. So what we're doing here exactly is each feature with each weight multiplied and summed up plus the b. So the sum goes like, this is the sum exactly, and the plus b is a constant. And then we squeeze it through some sigma function, and we'll come to that later on. Why is it important? One simplification of perceptron is this term b, the bias. So we basically extend the vector of weights by 1, and it now includes the b, which means we have to add the 1 to the input vector, as we just saw 2 slides ago. So I'm coming back here. We added this 1 to the input vector. So our new input is n features plus 1, and we add the constant 1, and we call it tilde x. And again, the output unit is the pre-activation is again simply multiplying each weight with each feature. So a linear combination, and we put it through the sigma. So this is just very fine-grained simplification of the perceptron, where we just get rid of the b completely. And the perceptron is a function. So we have some input, which is an n plus 1 dimensional vector, or n dimensional vector plus this single 1, and we output a number, a real number. And since this is a binary classification task, we want to output something which is either 0 or 1 at best. The vector, the weights, the vector are the parameters we want to learn. So we want to learn these vectors, these parameters w from the data, and how the training data are represented. So it's looks very straightforward. So we have a couple of n examples. So this is one example, and it has a vector of the inputs associated with the output value. So this is what the function is producing, or this is the gold label. So we call it gold label, and we have n of these. So it's a set of training data, and we want to optimize our function such that if we, so our function is f takes these parameters. So this is the input, these are the parameters, and we want to make the difference between what our function produces and the true gold label as minimum as possible. So we're fitting a function to data points. And this is one special case of a loss function, which is called squared loss. So we want to make sure that this function has some nice properties, such as it's differentiable and non-negative, so we can find the minimum easily. How do we minimize this function? So how do we find the best? We're actually trying to find the best parameters. So this is find best W. We use techniques called stochastic gradient descent, and we'll get to the details in the next lecture. And the perceptron, as I said, is a binary classifier. So we want to output it either 0 or 1. And how we do that? Well, there's some thresholding function. If the input of this sigma is lower than 0, we just say it's 0. And if it's greater than 0, we said it's 1. So we're splitting, in 0 we're splitting, saying, okay, whatever is negative has the label 0, whatever is positive has the label 1. So if we have two inputs, like two neurons, and the bias, then this decision boundary is basically a straight line. I'll show it in the next example. So, okay. So for example, so this is not NLP, this is, let's say, some classification of dogs and cats based on their two features. So, we have these features, feature size and feature domestication. And these features are in the feature vector. So these are real features. We have real numbers. So it means the input x is in 2 dimensions, right? And the larger the domestication and the larger the size, the better chance that's dogs, and the smaller domestication and the smaller the animal is, the bigger chance it's a cat. And since we have linear function, so we have a line in 2 dimensions, we can draw a line between these two classes, given these are the training data, and we then say, whatever is below is a cat, and whatever is above is a dog. Okay, so nothing else. So we have these dots, and we want to learn a function that is a linear line, or it's a line between these two classes. So Perceptron can do tasks that are in this form, that you can draw a line between these classes, between these two classes in the dimension, in the feature space. So let's have two sets, x0 and x1 of these points of this data set. So x0 and x1 are linearly separable. If there are some such real numbers that we can, so it's basically what it's saying, we can draw a line such that below the line there is one class and above the line there is another class. So this makes the task linearly separable. Not all tasks, well, actually very few tasks are such an easy linearly separable thing. So if we come back to dogs and cats, we might have this example. So again, we might have, again, two features, so the same features, size and domestication, but we have the following problem, so, the larger domestication and the bigger size, that's fine, the more it's likely to be a dog, but then we might have a super cute, domesticized, super huge cat, like this one. So this is my parents' cat, like, very cute one, very big one. And then whatever you draw here, a line, as we had before, will be wrong, because then it can't classify this cat. So what you would need maybe instead is something more, okay, like, so these are dogs, and yeah, and maybe these are cats, but you can't do that with a line. So you have something where you have like X or, exclusive or. So either it's domesticated, it's small domestication and small size, or and so on. So different splitting of the feature space. So the perceptron was very simple, and now we're going to more, let's say, complex architecture and to the very heart of deep learning, which is the depth. So first extension is that previously we had only one output, which was the dot product. So previously you would have something like I1 and all these features. But we might have multiple outputs of this transformation, and now it makes it a so we wouldn't have one vector of weights, but we would have a matrix of weights. How can we understand it? Basically, is a linear mapping. So we are mapping from a dimension here 4 to dimension of 3. And mapping between dimensions or linear maps is something we know from linear algebra. So we have matrices for that. So matrix is a mapping from one dimension to another dimension. And so the weights are here now in a matrix, and we have x, the input, as a row vector, and each column in W is the weights for the particular output. Okay. I might give some example here. So, okay, let's have, here we would have x, x1 up to x4 as a vector times the matrix W. So now it would have 3 columns. So this would be size 3 and 4 rows, because you're multiplying this one would give you the first number, so the y1, and then again with the second column the y2, and with the third column would give you y3. So nothing more than multiplying or projecting one vector to another space, and it's a linear projections because there's just a linear map, which is the matrix. In deep learning, the depth comes with the number of layers. So we are extending our example now by adding one more, so to say, layer, and we call it hidden layer. So previously we would have only one input and output, but now we're stacking that. So there is, input goes to hidden layer, then it goes to the output. And this architecture is the most well-known architecture in neural networks. It's called multi-layer perceptron, because basically it is somehow perceptron, because we're multiplying inputs to form the output in each layer, but we're stacking this layer next to each other. And what I'm showing here, the number of the neurons in the hidden layer, it's an arbitrary decision. So there could be more. There could be even like larger than the first one. There could be only one if I really want, and so on. So these are more design decision of the network. It's up to me to decide what I want to do, and also like a little bit of empirical experimenting. And what exactly is doing this in computation is, again, for each next network, for each next layer, we're taking the inputs. So here this is the vector x, combining with the first W weight matrices and the bias term. So we get a linear combination, and we squeeze it through this nonlinear function. So this is nonlinear. Why are we doing this nonlinear transformation? I hope we'll get back to that later, but you can understand it as, if you stack many layers of linear transformation, what you get is still a linear transformation, because it's like multiplying 2 matrices or 3 matrices, you get a matrix, and a matrix is a linear transformation, so you can't get any non-linearities in there. So if your problem is linear, then it's fine. If your problem is nonlinear, then you need some non-linearity. And what this non-linearity is doing, you can somehow imagine this as a squashing your vector space, squeezing it somehow and moving things around, so it looks differently. It's not like linear mapping, it's somehow squeezed. which could be easy to imagine in 2 dimensions. It's super hard to imagine in multiple dimensions and with more depth. But how I understand it's like you map one dimensions to other dimensions linearly, so everything will have some linear dependencies. They will keep the same, in the ratio, but then it will be squeezed somehow and pushed somewhere and making it nonlinear. Okay, so the sigma is applied element wise. So for example, if we have input vector v, the sigma v would be sigma applied to each input individually. This is important. So sigma is some function which takes a real number and outputs a real number, or takes a vector and outputs a vector, but it's applied on each of the elements. So this was the computation for the first layer, but for the second layer, it's the same thing. So it takes the input, which is now the output of the first layer, multiplies by some weights, adding some bias again, and squeeze it through some nonlinear function. And by stacking these, you're projecting your initial vector space through these nonlinearities to some vector space that will make it linearly separable. This is the idea. So linear function, neural networks are functions. They have an input and output, and there are stacked functions that in this form. So one function takes the input and produces the first output, then it comes as input to the next function. So basically we're stacking the functions deeper and deeper from the input to the output. And we have these parameters w and v and so on. When we generally talk about neural networks, we say, okay, these are somehow hidden in one variable theta, and we say these are all variables, so all the w's and v's are there. This is like very high level view on neural networks, because what we care is some parameterization of the network, of the function, and then we care about the input. So it takes the input, parameterized by something, and outputs some value. So we mentioned already activation functions, which are the nonlinear functions. So let's have a closer look what they could be, apart from just saying it's a sigma or something. So linear activation is fine. It's basically doing nothing. So provided you get the input ax plus b, it outputs this linear combination, or let me put it like that. So if we have this pre-activation is ax plus b, then the activation, linear activation, would be simply this. So ax plus b as well. So there's nothing nonlinear, no op, so to say. And as I said before, if your neurons have linear activations, so basically just weighting the input linearly through a matrix, then it's computing again a linear function. So we can solve nonlinear problems with that. But now comes something really useful, finally something which makes a little bit of sense. So we have a logistic activation called sigmoid. And if you look at the graph, basically, before jumping here to the formula, if you look at the graph, what is this sigmoid doing? Let's take the blue one. So it's parameterized by some a. And if this is simply 1 over 1 plus a to minus x, it looks like this blue one thing. So what is it doing? It's taking any real number on the x-axis and creating something in the range of 1 or 0 to 1. So it's squeezing everything to 0 and 1, right? Linear function would basically take infinity from infinity to infinity to infinity, but sigmoid takes infinity to infinity and squeezes into 0 and 1. It's very interesting. It can have some consequences. Why is that so? We have some parameter a, which we might use or might not use. It behaves differently. So with higher a parameter, it's going more towards a step function. So everything which is below 0 would be 0, and everything positive would be 1. The advantage compared to this Perceptron step function is that this is differentiable. So you can get derivatives in any part of that. No matter how high the a is, you will still get some derivatives. That will be crazy and big or super low. Here the derivative would be 0 most of the range. But you can differentiate a function, which is make it easier for learning later on. So exactly, this is the point. Gradient is problematic for large values. So we'll be using gradient in these functions for optimizing. And if you look at it, the function saturates to 1 or 0, and gradient is the tangent, or it's the change at the place. So here the gradient could be, for example, this function, but here the gradient will be always 0, which might be problematic. Another similar activation is tangents hyperbolicus. It's very similar to the sigmoid, but it's now the range of the function is from -1 to 1, so it's centered around 0, which might be useful in some cases. But again, as the input gets larger or smaller, the gradient becomes just negligible or 0, which might have some consequences. So there is some new one from, I would say, 2013, 2014, called rectified linear unit activation. And it's basically saying that, so if the input is positive, it's just in the identity function. If the input is negative, we just return 0. So why is that interesting? Well, it just says, well, okay, I can get the gradient of the input no matter how large the input, no matter how large is that. But still there is some non-linearity here, so I'm just cutting off everything which is negative. So it's a very interesting function, which makes the gradient not saturate for large values. And it's computationally efficient because getting gradient of linear function is super easy. And it converges faster. So there is one caveat here, and this is this point. If you're thinking about gradient, so you can get gradient here, you can get gradient here because it's 0. How about this very point? So basically you neglect it. So if there is a 0 in the input, this function doesn't have a derivative at 0, but computationally or by engineering, you just say, well, okay, it's 0, so you can neglect it and it's fine. And another one is leaky rectified linear unit. Exactly. So as compared to the previous, we'll still keeping, the right hand side is the same. So again, it's the identity of the input, but then for the negative input, we multiply it by some small value. So if the input is negative, we're saying, well, we're making it smaller and smaller. And it makes actually the gradient, computable for the entire domain. So it will never be 0. And it's just then, an experimental setup to find out which activation function works better for my task. And now we're coming to the most interesting, I would say, activation function, because so far the activation function was only local. So it was applied for each of these output units separately. But now with softmax, we're treating all of them at once. So the whole layer is pushed through the softmax function. Why is this important and where can we use it? So in classification to multiple output classes, so for example, sentiment classification of movies into positive, negative, and neutral, we would like to have the output to represent a probability distribution of these labels. So we would have that all three values would sum up to 1 and being non-negative. Something like, basically probability distribution is a histogram. So we would have I1, I2, I3, and something like this. So, 0.1, 0.7, and 0.2, for example. And it sums up to 1, and it's non-negative, and you can see it as a probability distribution over these labels. And then in classification, you would say, okay, well, the one with the highest probability is the output, is the actual output, and it's, in this case, would be, I don't know, like negative. So it's up to us to design that. It could be arbitrary, but we want to have this nice property. How can we do that? So let's say that the Z1 is the input value for each of these nodes, the pre-activation, so to say, after the linear transformation. So we would somehow want to normalize these three values so that they sum up to 1. We could do that by simply summing up, taking the sum and taking one value and dividing by the sum. But there are some better ones, better functions with better properties. And this is the sigmoid, or this is the softmax, which is taking the exponential of this. So taking, for example, for the first value, it would exponentiate the first input and normalize by exponents of the full layer. So again, very generally now, for each of these outputs, it takes the input of the node, exponentiate, and then normalize for all of them. What's the difference between just normalizing by the summation and normalizing by these exponents? You can try it out, but it's basically squeezing it's squeezing the values to the extremes more. So it's pushing low values even smaller and making big values even bigger. So it's better for the classification then. And here's the softmax again. It depends on all the units in the layer. So you have to take all of them. The sigmoid or the other ReLU and so on are applied on each of the neurons, but softmax takes the whole layer. And it makes a probability interpretation, as we just saw. So it assigns probability to each of the neurons. And actually the name of the softmax is if you think about it, why is it soft? So some sort of soft maximum? Is it giving me the maximum value? And is it soft so I can differentiate it? It's a misleading name. It's actually badly chosen name. It's not a smooth maximum, but it's rather smooth arcmax. Because it's telling you which, so if we have this histogram again, I1, I2, I3, so this would be, our histogram or the probability distribution. It's telling you not the actual value of this, what is the value, but it's telling you which of these, so the argument max, which of them is the maximum one. So there is one function actually for softmax, soft maximum, and it's under log sum exponential. So again, differential, then it would give you the actual number. But we are in classification are interested in which class has the maximum probability, and this is what we are interested in under the misleading name softmax. And it brings me to the end of this first lecture. Wow, we went fast. So what we did, we started with some organizational issues, administration. We look at the history for some reason to understand like everything lives in a context, and science is not done by individuals, but by communities. And we also looked at some issues in NLP and why they might be hard to solve. We talked about the perceptron, and we looked at some basics of deep learning, such as the activation or multi-layer perceptron. Thanks a lot for watching. If you have any questions, any comments, anything unclear, drop me a line, put it into comments here or on the Moodle or Discord, and I'll be happy to see you next time.